lineals, right? It's still fun.
Yeah.
Yeah. I mean, it's tough, right? It's still, I don't think much about it.
Yeah.
All right, because it's very tough, let's try to do this class again. So what we are doing, I think, actually literally for 2 lectures in a row, and we never finish anything. And it seems to me we're going to do another repeat and only go 2 slides beyond what we covered the last 2 lectures. And by that time, it's going to be Thanksgiving, and I'm going to be in Hong Kong, and that we will call it the end of the semester. All right. So what we do is we are discussing extending sequential Monte Carlo. Well, actually, sorry, we're trying to extend important sampling to problems in dynamics and leading to what we call the sequential Monte Carlo methods. So the slides actually, this is a new set of slides, but it has the first 20 slides or so are similar to the ones we covered. So let me go extremely rapidly for those that were not here. Remind you the notation. When we try to sample from a distribution pi, we take samples from the distribution pi and we define what is called the empirical measure of the distribution in terms of delta functions. Okay? Hopefully, by now this notation is very familiar to everybody. So this is an approximation of a distribution in terms of samples. It's a very powerful notation, and you notice all the samples are with the same weight, 1/n. Okay? So if you try to calculate estimators like the expectation of a function, and you use instead of pi the approximate, the empirical measure pi hat, immediately you can see by putting this delta function inside the integral, you actually get your classical Monte Carlo estimator. Okay? So this is very important notation, and then effectively we get the estimator in a natural way by approximating pi with pi hat. We have seen, so let me put all of these things up, we have seen that this estimator is unbiased, all right, and also we have seen that the variance is 1/n, and it's independent of the distribution of pi, okay? So independent of the dimensionality of pi. Something that also we discuss is that somehow if you're only interested in the marginal distribution xp, not the whole vector x there, the only thing you have to do is use only the delta functions at the particles xp. The rest, you basically have integrate them out. So the idea is once you have this delta function approximation, the marginals come for free. All right, we continue rapidly from there. We said we cannot really approximate, we cannot really take samples from pi. In general, pi is very complicated. Maybe it's a computer code, so what we do is we have an importance sampling distribution Q, and rather than sampling from pi, we sample from Q. And the requirements on Q were very, very minimal. Effectively, we said that where pi is positive, Q should be positive. Q, the same way as when we did these accept-reject methods, need to be heavy tails above the tails, basically, of the distribution pi, but nothing major. And we also said that pi is not known up to, basically we don't know the normalization factor of pi, so we really need to be able to manipulate only gamma, and gamma is the unnormalized pi distribution. So if pi is a posterior, for example, the only thing we know is the joint distribution, okay, of, you will see shortly when I do the dynamical problem, but we will assume we only know gamma, not the normalizing factor z. All right, so this is the definition we introduced of the weights. The weights, when we do important sampling, is the unnormalized part of pi divided by q, and you can immediately see that pi is written as w times q divided by z. You can see this immediately because w times q is gamma, so gamma over z. But this is a nice starting point, because in some sense, if we have samples from q, in this approximation, in this equation here, we can substitute q with the sample approximation of q, all right? And then we will see how the sample approximation of pi is going to look like. So the idea of importance sampling is we don't take samples from pi, we take samples from Q. So the approximation of Q is exactly as before. So if you plug in this Q inside this equation for pi, you're going to get a Monte Carlo approximation of pi, and there is the answer that we have seen before. You get basically a weighted sum of delta functions. Okay? So before that, these delta functions had the weights the same, 1 over n, but now we have Wi for each particle I, and the notation we use here is capital W are the normalized weights, and little w is their normalized weight, so little w divided by the summation of all the w's gives capital W. I noticed this morning I was looking at a few slides here and there were some mistakes. I tried to correct them. In reality, things should not make big difference because capital W is proportional to little w, but some of the equations, there is a missing factor there because I did not account the difference between little w and capital W. Anyways, capital W, the normalized weights. The idea here is with importance sampling, we have delta functions, but the weights are not the same. And effectively, the weights, what they do is they account for the fact that we didn't sample from pi, we sample from Q. So they account for that discrepancy, if you like, in the sampling process. All right? And we actually can compute the normalization factor of the distribution pi quite easily, and this is an extremely powerful formula. So remember, the normalization factor is the integral of gamma dx. So what I do is I divide by Q and multiply by Q. So these are the weights, all right, the normalized weights. And now what I do is for Q hat, I use the Monte Carlo approximation of Q hat. So immediately you can see that if you want to get the normalizing factor is 1 over n the summation of the unnormalized weights. So this idea of model evidence that we were doing earlier in the course for model selection comes extremely in a very straightforward manner because with Monte Carlo methods, you sum this and there is the normalization factor. Zero cost, basically. So once you have done the approximation of pi, summing these things up, 1 over n gives you the approximation of z. All right? So if you use this important sampling approximation for pi, you can get the expectations exactly as we had before. The only difference is instead of 1 over n, we have now the weights. These are the normalized weights, capital W. And we mentioned that this estimator is biased, right? You don't see this in standard books, but if you dig in, you will see there is a small bias, okay? The notations here, I think I corrected them in all the slides. This is an expectation with respect to pi, this is capital W, and the variance is exactly what you expect. The only difference here is there is a capital W in both terms inside, okay? I mean, the idea is obviously you have to account for the fact you don't sample from pi, you sample from Q, and that W accounts for that difference. So there is a bias, the variance more or less the same as before. This bias term is, for n greater than 1, so if you have n equal to 1,000, it's negligible, but for small samples is important. All right, the normalization factor, you can show that it's unbiased, so this estimate that I showed you before is unbiased, and the variance is given by this nice formula. Okay, extremely very powerful, basically because if you really want to calculate the model evidence and you want to have some error estimates, the idea is the error in the estimation of Z is already available on this nice formula. All right, we said that all of these things to happen, sort of a good bottom line criterion will be that the weights need to be bounded. All right, so gamma over Q has to be less than infinity. And then we proceed to the dynamical problem to apply these techniques. Now, I realize there are no slides on the dynamical problem, so my apologies. because then you have no idea what I'm talking, all right? So, so basically we were discussing what's called a state space model, okay? And you can think of a state space model like a Markov chain, where you have a transition from a state x1 to x2 to x3, and I provide you a law of how to go from one state to the next, okay? Now, in the state space models, this transition, this chain, it's unknown, it's hidden. So I don't really know the states x, but what I know is some noisy observations of x, that I call them y. And I give you an observation model that at each time it tells me what's the probability of y given x. So what we want to do on these state space models, which are universal, they come everywhere in every problem that involves dynamics, we want to compute at each time n, we want to compute the posterior of the states x from 1 to n, all right, given all the data from 1 to n. And so effectively, if we're going to do this with Monte Carlo methods, we need to be able to work with the normalized posterior, which is the joint distribution of x and y. All right, so in this state space models, x is the hidden states, y are the observations, the data, and this is the normalized part of the distribution. This is the normalization factor that we may be able to compute as well. And why do we care about the dynamical problems? Because they are universal. If you have data in time, this is the easiest model to start with. That's one, and also there is lots of interesting aspects here, because you want to be able to approximate or take samples from these distributions at different n without having a cost that increases with time. So imagine if you start right at time 1, you have only x1 and y1. At time 2, you have x1 and x2. At time 3, you have x1, x2, and x3, because you want to update all your states. Okay? So you don't want to do this calculation in a way that increases the computational cost. And if you do it with simple Monte Carlo or important sampling, basically you are doomed that eventually, after a few time steps, this thing will start giving you garbage. Okay? So let's see first the garbage methods, the standard methods, to remind you the notation. If you go and you sample directly from the posterior, so this is our standard Monte Carlo method. These I are the samples out of this posterior. Then the Monte Carlo approximation of P is given like exactly as before. And this is our estimator. If you want to find the expectation of any function under this posterior, using the Monte Carlo estimate in terms of particles, you get basically your standard Monte Carlo things. And again, unbiased, and the variance is given by this nice formula. We keep seeing these things because I know even those who were in the class listening to me 3 times saying the same things, if I ask them with closed notes to write me down this equation with the correct notation, they will basically have a hard time, correct? Yes, no? Say yes or no. All right? But unfortunately, you like it or not, every single thing here has a significance, right? So what is the hat means there? I see a hat there, right? It says the variance of this estimator, and I see a hat. So what's the hat means? I didn't put it there just to decorate it. So what's the hat means? I am taking the expectation. This is an estimator. I don't have access to the true posterior. So what is this posterior? Is the empirical measure. And it's the empirical measure when I have collected how many data? N. Okay? All right. So there is a meaning to these things. Okay? So this is the exact estimator. This is the approximation. And we know this is the central limit theorem. But basically nothing else but the variance is 1 over n, the true variance. And as I mentioned before, if you want to marginalize, it's straightforward because at every time n, you integrate all the delta functions in from 1 to k minus 1 and k plus 1 to n out. You get 1, and then effectively directly you have a Monte Carlo approximation of this distribution, okay? So xk is one of the variables, okay? Given the data 1 to n. All right, so important sampling again. For this problem, we cannot sample from this distribution, it's complicated. So the thing is, we're going to introduce an importance distribution. So the notation is identical to what I had before. It's adjusted to this particular dynamical problem. So this, we approximate the true posterior. I'm sorry, we don't approximate anything. This is exact. So the posterior is equal to the weight. The weights are the anormalized posterior, so it's the joint divided by Q times Q divided by the normalizing factor, okay? You can see this is straightforward, right? Because W is gamma over the Q times Q, and gamma over the normalization factor of the distribution gives you the actual distribution. All right? So what we do is we are going to sample from Q, and in the formula that I had before, instead of Q there, we're going to put the empirical measure of Q. And so you get these delta functions, top and bottom. And when you do the calculations, you get this fantastic formula, the approximation of the posterior. It is these delta functions defined from samples that you took from Q, but instead of 1 over n, these samples have weights that are, these are the normalized weights, capital W n of I. Again, the notation may look strange. Little n refers to the fact that we're looking at the posterior at time n, and little I is how many samples are we taking, okay? And the number of samples is from 1 to n. All right, exactly as we discussed in the generic case, if you want to get the evidence, basically the sum of the anormalized weight divided by 1 over n is, it gives you P of y from 1 to n. Okay, if you look at the definition of the anormalized weights, right, it is the joint divided by Q, and I can write the joint using the product rule as pi of y from 1 to n, and then I have the true posterior divided by Q, so you can see the discrepancy comes from the fact that Q is not equal to that. So the idea is if I put Q equal to pi, that you see here, you get basically standard Monte Carlo. The idea is, can we actually come close to something that approximates this posterior but is not that posterior, okay? And that ratio basically would be the discrepancy that these normalized weights account for. All right. So I had mentioned again that when we use this estimator, this is an unbiased estimator of the evidence, if you like. And so a correction actually I did this morning, if you see in earlier slides, anywhere you see some estimation in terms of the weights -1, be sure that the weights are denormalized, because if I put a capital W there, I don't need this term. All right, if I put little w, then I need to have this term as well. Okay, let me keep going to find some essential things. So we said that the estimator is biased, right? So this is the actual bias of the estimator divided by 1 over n. Okay. Can you remind me, since everybody's following these lectures for too many times, why is this important sampling estimator biased? What is in the calculation that make this thing to be a biased estimator? All right, it's hidden on this slide. What makes this to be a bias? I don't want the details of mathematics. I just want to know where was the complexity coming that suddenly from this unbiased Monte Carlo estimators we get a biased estimator. So what is in here that make this thing to be biased? why this is, we were getting, when we do important sampling approximation for this distribution, or any other distribution, why the estimator comes to be biased. Because you can see from this calculation here, right, that the empirical measure for this distribution is the ratio of two Monte Carlo approximations. One on the numerator that involves this Q, and one in the denominator that involves this Q. So you have a ratio of two Monte Carlo estimators, so you can actually, when you do the algebra, this ratio makes the whole thing to be biased. If this thing on the denominator was not there, it would not be an issue, but because we divide to normalize, it's a ratio of two Monte Carlo estimators, so this makes the whole calculation biased.
So,
Yep.
So, why is that the case? Sorry. Why is the ratio of two Monte Carlos?
So yeah, so you remember this, look at this equation, right? This equation, it's sort of, it's exact, and it's written for a particular reason. So W is the joint distribution of X and Y divided by Q. So you can see Q and Q cancel, and then you have the joint distribution divided by the normalization factor, that's the posterior. It's exact, okay? So when I do Monte Carlo approximation, I, instead of using Q there, I am going to put the empirical measure of Q, the Monte Carlo approximation of Q. So that's one approximation, and then that's another approximation on the bottom. They don't cancel because the one on the bottom integrates X out. It's a normalization factor. All right, so you get the ratio of two estimators there. Okay, just in passing, because I corrected the slides, I think we're going to come back to these slides before. When you do important samplings, the variance of important sampling estimator is not the same as the variance if you were doing standard Monte Carlo, and you can actually show that the important sampling variance divided by standard Monte Carlo variance is 1 plus the variance of the weights. This is a very important calculation, okay? This is an approximate result, but at the end of the day, if you, let's say you were doing standard Monte Carlo, you were sampling from the exact distribution, which is this, and you take, let's say, n samples from this distribution, and then you go and you take n samples from the important sampling distribution, then it comes that this, from this n samples, a small part, m, is equivalent, it's sort of like samples coming from a standard Monte Carlo estimator. So basically, n-weighted samples from this distribution are only equivalent to a small percent, that's a number m, that are coming from this distribution. All right, so let's say you go and you take n samples with standard Monte Carlo from this distribution, and you take 1,000 samples from this distribution. Well, out of these 1,000 samples, about 500, let's say, would be equivalent to standard Monte Carlo. And the ratio is defined basically by the variance of the weights, okay? So this calculation is extremely important, right? Because how effective is important sampling depends on the variance of the weights, okay? If the variance of the weights is very high, means you're wasting too much effort about nothing, and so the simulation is not going to be efficient. So something that you should use in practice when you want to figure out how efficient is your important sampling calculations, you have to calculate what is called the effective sample size M. This is basically the same M as here. And the important sampling, effective sample size is the sum of the normalized weight square inverse. There was a mistake on the previous slides that I think I corrected them this morning. So this is capital W, so it's the normalized weights. This is a relation actually of this term here with the variance of the normalized weights. And this effective sample size is between 1 and n. So if you're very close to 1, it means you're taking n samples, but in reality only one sample is useful. If you're very close to n, then it's like doing standard Monte Carlo, and you can see if the weights here are 1 over n, the way you do in standard Monte Carlo, so you're going to have 1 over n squared times n, you have 1 over n inverse, so the effective sample size is equal to n. Okay? So when you do simulations, this is a number you need to report basically. You need to say what is your effective sample size, and as we will see on Thursday, and I will show you lots of nice animations, if this effective sample size is below a threshold, what you need to do is you need to resample to get rid of particles that have very small weights. Okay? And you are going to have to do this in the homework, right? And you're going to have to do it right, because last year nobody did it right. Okay? Because it's sort of, when you do it, you'll be so happy that actually you understand what is going on, and you can actually use it in your research. Okay? So I'm going to come back to this later on. All right. Don't need these things. Okay. So here is now, we're back to the business to discuss new things. The methodologies that I gave you, they are not efficient, right? You are building approximations of the posterior every time, starting from scratch. So eventually, things will blow up. And even if they don't blow up, you know what's going to blow up? The variance of the weights is going to blow up. Right? So if you do nothing, the variance of the weights basically is going to blow up, and you will not be able to continue. So the idea here is, if we have an approximation of the posterior time n-1, can we reuse it to come up with an easy approximation for the distribution of time n? And of course, the idea here is that the distribution at n-1 should not be very much different from the distribution of time n. So how do we reuse this so we don't recompute everything from scratch? All right, so let me go directly to how we're going to work. So we start at time 1. And remember, at time 1, we have x1 and y1. So x1 is the state, y1 is the measurement, right? So this is the true posterior. So we need to get an approximation of this distribution, all right, of P of x1 given y1, okay? And we're going to take n samples, but the samples are going to come from this important sampling distribution Q. Okay, so you start with some Q of x1 given y1, some easy distribution. You take n samples from Q, and then, as we did before, the approximation of Pn, the posterior time 1, is going to be basically the normalized weights times these delta functions. Okay, and again, maybe in another course I will tell you more, but you notice here I put this dx1 there to make this the notation more compact in terms of probability measures, because when you write something in terms of delta functions, people tell you, what does that mean? Right? It only means things if you apply it to some dx's, but so this is the notation standard, but let's not bother about it. Okay? So we approximate this in terms of these delta functions with these weights defined like that, and similarly we approximate the normalizing factor at time 1 like this, and the weights, this is important, is the unnormalized posterior divided by the important sampling distribution Q1. Okay? Nothing yet important at time 1. This is what I do. Define these normalized weights, approximate Pn with delta functions weighted, all right? And this is the normalization factor, and the weights, I want you to remember this, the weights are the normalized distribution at time 1 divided by Q1. All right, so what are we going to do at time Q2? At time Q2, we want to approximate this posterior. So now we have moved in time, and I collected data y1 and y2, and I want to update not only the state x2, but there is a state x1 there, okay? So these are x from 1 to 2, given y1 to 2. So we're going to introduce an important density that looks like this. And what we're going to do is, we're going to restrict the form of this important density to make life easy, and we're going to make it to look like this formula that you see here. So look at it and tell me, why is this significant? So the importance distribution here has the previous importance distribution of time 1 times Q2, that is x2 given all the data in x1. So why is this, what makes this equation nice? It tells you when you're at time 2 and you want to take samples from this distribution so you can approximate this, you don't really have to update x1 because x1 is sampled from Q1 and we already have done that. So we're going to reduce the samples of x1 we got at time 1. The only thing we're going to do is we're going to update x2 given x1 and all the new data. Right? Okay? So this is the idea is if we had, let's say, samples xi of time 1, we're going to reuse the samples and then sample from Q2 to get samples x2. In some sense, right, you can think, you know, I mean, you say, well, okay, the state at time 2 is some new random variable, but the way you would like to start thinking on these dynamical problems is that you took this particle x1 of I and you move it to x2 of I. Literally, that's why these methods are called particle methods, because you say you are here, now you are there. Okay? And I will show you this with little movies, if not today, on Thursday, on how it's going to work. All right, so we move x1i to x2i. And the question is, what happens to the weights? Can we compute them incrementally also, so we reuse the previous weights? The answer is yes. So look at this. Do you agree with me that this formula here is the definition of the weights at time 2? This is the unnormalized posterior divided by the proposal distribution, and you remember we wrote the proposal distribution as Q1 times Q2 like that. So what I have done now is I multiply and divide by the unnormalized posterior at time 1, and what do I get? This first fraction there, don't you think it is the weight at time step 1? We already computed that weight. Okay, so which means we will keep track of the previous weights at least. And then we have this equation here that involves the joint, the unnormalized posterior basically at time 2, divided by the unnormalized posterior at time 1, times Q2. And this we are going to approximate using the equations from the state space model, right? Let me see if I can see the formula. All right, there was a lot of nothing in between. So effectively, we can generalize, use the previous weights at time n minus 1 to update to the weights at time n. And the factor, that becomes the incremental factor, if you remember on, you know, when I was talking a few seconds ago, there is the joint posterior at time n, all right, and then the joint posterior at time n minus 1. If you expand this in terms of your dynamical and observational system, the only thing that comes out, the ratio of those two distributions, is basically the transition model from xn minus 1 to xn, and then the observation model that gives you the probability of yn given xn, and then you have this incremental importance distribution on the denominator, and that's basically the standard formula to starting doing sequential Monte Carlo methods. So the idea here is you will do this incrementally, you will reuse the particles from the previous time, you will reuse the weights from the previous time, and then somehow with this incremental weights, okay, you'll be able to update the weights from n minus 1 to time n. And where are the particles xn of I are going to come? You remember they're going to come incrementally from this proposal distribution. So using, you know, the previous particles, all right, and the measurements at time n, you're going to have a proposal distribution Qn, and then you're going to move these particles to xn. At this point, okay, and there is lots there, it looks not very practical because you notice to implement this, you have to keep the particles from time n to n minus 1. It's disaster. Right? Keeping all the particles like for 1,000 times steps, you know, it's a disaster. Okay? Do we need to do this? And that's where we're going to start doing some approximations. And here is the approximations. How about if instead of using this incremental proposal distribution, we approximate it with this nice formula there? And tell me if you have any objections. Does that look physical to you? It says, you know what? If I know the state xn minus 1, all right, I don't really need to know the states x1 to n minus 2 to define xn. All right, if I know the state of the previous step, that's enough, okay? And then it says, well, look, I have data here from y1 to n minus 1, but I don't really need them because this data are really defining my state xn minus 1. So all the information from that data is on the state xn minus 1. So the only thing I'm going to keep is yn and xn minus 1. And so basically, when you want to go from n minus 1 to n, you don't really need to keep all the particles at all previous time, only at time n minus 1. And then if you, if you sample from with a given n minus 1 and given observation yn, you can sample from here xn, and effectively your new samples at time n, they're going to be your previous, for each particle, right, are going to be the previous values that you computed at time n minus 1, and then you go and you say, and now I have a new state xn as well. Okay, so you're already using everything from before, and then you augment it with something that you sample from this distribution up there. So very, very efficient, and of course, not the end of the day, because people like even simpler and simpler algorithms, so we will see how the simpler algorithms are coming up. But again, I want you to remember that at each time, we are going to be sampling xn from this distribution, from this proposal distribution. And of course, you will ask me, and what is that proposal distribution? You tell me it depends on yn and xn minus 1, but it can be anything. So what should I use? All right? What you use has different names. I don't want you to bother about it. Statisticians use one name. People in machine learning use something else. In finance engineering, where they have lots of dynamical systems, they use something else. I am sure in ecology, they must be using something else. So it's unimportant, okay? So the only thing I'm going to remind you is the weights will be the previous weights and the incremental weights, and the only difference here is I substituted this approximate proposal distribution that I discussed before. So if we somehow can compute this, or we know what should we put here, F it's easy to compute, G divided by Q, and then we can update W. So let me give you the algorithm actually. If you understand this slide, even if I got you confused up to now, this slide has everything we need to know. Nothing else is needed. Time 1, you sample from the proposal distribution Q of x1 given y1. So the approximation of your posterior is given in terms of these normalized weights, and the normalized weights are basically this is the normalized posterior divided by Q. And I remind you at time 1, there is no evolution yet, so you really have the probability that from where you sample state x1 and the observation model of y1 given x1. Okay? Actually, I realized there I should put given x1, okay? And type on slide 37. And then at time 2 and further down, you're going to sample, let's say at time n, you're going to sample from this proposal distribution, and you're going to compute the incremental weights given by this nice formula, and then the approximation of the posterior is given this in this nice way. So you are using to compute this, you're using the weights from the previous time, you're updating them with this factor, and all the sample paths basically up to time n minus 1 are fixed from before, and the only thing you have to do is add this path to time n, all right, which is given by that, and that's it. That's the algorithm. So if you're going to write a computer program, basically this is how it's going to look like. Now in reality, you can program this in a few lines, and it's already there most probably in different statistical packages, but when you try it in one problem, you realize it may not work, right? I mean, after a little while, the results are all over the place and blow up, and you say, what's going on? Don't expect it to work, okay? Because for things to work, you need to do some tricks, okay? So the nice thing that I want to mention before we discuss specifics of the algorithm, right? The cost of the algorithm, the complexity, does not increase with time. So this is very nice, right? This is what we wanted. We wanted something that at each time step, the algorithm has the same cost. It does not increase with time, okay? Most important, the algorithm is parallelizable, so you can actually think of getting all the samples in parallel, calculating the weights then all together, and so it's extremely efficient. And I don't know if I'm going to have time to do this later on. This algorithm is not only used for dynamical problems, it's used even for static problems. All right, so you just need to imagine on how is that possible, but you can use it for everything, but certainly for dynamical systems is the standard way to do it. So what do we use as importance distribution? This is what I want to tell you today. So we're going to, obviously we're going to have to minimize the variance of the weights or come something close to it. And I'm not going to do the derivation here. It's actually straightforward. Let me just say, if you use, so this is the big importance sampling distribution, right? You really, if you want to minimize the weights, you have to take the exact posterior, which is not tractable. But in this calculation, maybe you should look at it because to see that you understand the notation. If you make this importance distribution equal to that, then indeed the variance of the weights is 0, and so the algorithm in many ways is optimal, but that's not very useful. So let's see what we can do here. I'm writing the weights up to time n. This is the normalized posterior divided by the importance sampling distribution. And I remind you the importance sampling distribution, we approximated incrementally the way you see here on the denominator. This is time n minus 1, and then this is the incremental, where we did some simplifications and we got rid of few terms. And on the numerator, I just write this joint using the product rule as P of y times P of x given y. Let me do a little bit more algebra. This x from 1 to n, I can write it xn, and x from 1 to n minus 1. There is a reason, because I want to get some recursive equations. And so will you agree with me that this term here, don't bother about the condition on y, so you can see what's going on. You can really write it as x of 1 to n minus 1 given y, times of p of xn given x1 to n minus 1 and y, right? There's nothing fancy. The denominator is exactly as before. And so what you get is, you actually get this term, and in this term there's no xn, all right? There's no xn. And on this last term, there is p of xn given xn minus 1 and yn, and q of n, xn minus 1 and yn. And you remember, we're asking what are the optimum, how should we select q incrementally so that we minimize the variance of the weights, and the calculation basically that involves xn is in the last term. So what is the optimal then? The optimal values, what's the optimal q I can use looking at this equation to minimize the variance of the weights? As unrealistic as it may look like, what's the optimal q I can use in here? Say it again?
Maximum.
The maximum? What maximum? So the optimal would be to actually use Qn equal to this P of xn given xn minus 1, comma yn, all right? Because this will eliminate basically any change on xn. This is a constant value, so the variance incrementally will be 0 basically. Okay? So here is the optimal, all right? The optimal choice of importance distribution. This is very, very important statement here. And if you use the basically Bayes' rule, if you like, okay, you can rewrite this equation like this. All right? Can you see this? So what is involved here? So keep, you know what, do the following thing. Keep this as constant out of your head. Reverse now yn and xn. Will you get P of yn given xn times P of xn? Right? P of yn given xn and P of xn. And now you put back the conditioning xn minus 1, and in the denominator you're going to have P of yn. Okay? What is P of xn given xn minus 1? Is the dynamical model, how the system evolves in time. And this is the observation model. If I know xn, that defines yn. I don't need to know xn minus 1. So this is the observation model. And on the denominator, you have, it's the normalizing factor of the numerator. So it's really this integral that you see there. So this equation is the optimal proposal distribution that you can use in sequential importance sampling. This is basically the best you can do is to use, once we have done this approximation, this is the best to do to minimize the variance of the weights. It looks very easy to calculate, right? But you have to keep in mind two things. There is an integral, and you have to keep in mind that maybe this f and g are non-linear and maybe non-Gaussian in real problems. Now, if it happens that this is Gaussian, and I'm going to do an example, then this thing comes to be Gaussian and you're in business. If it is not Gaussian, then you may have problems, okay? But this is the optimal distribution, and it looks wonderful, right? Because it's the product of the dynamical model times the observation and some normalization factor. So with this actually, if you remember the equations that we had for the incremental weights, you remember the incremental weights, it was f times g divided by this proposal distribution, the incremental one. So if I plug in this to be f times g divided by this integral, then the incremental weights is actually this integral. Right? A very nice formula, but again, this integral is nasty. If I have to compute an integral at each time, that can be extremely complicated. Literally, if you want to remember one thing, right, just remember that we're going to be sampling xn incrementally from this proposal distribution that is f times g divided by some normalizing factor, and somehow the incremental weights, they come out to be this normalizing factor because f and g cancel out, okay? And you can actually prove, there is theory on this, that as n goes to infinity, this thing converges to the true value, so it satisfies everything. The cost doesn't increase with time. You don't have to worry about the variance exploding. But again, it is not practical if f and g are not Gaussian. That can be complicated. So here is another way written this for each particle, right? So for each particle I, these are the weights that you calculated at the previous time step times this integral, right? So xn minus 1, you're going to put your previous particle. This is your observational time n, and the idea here is you have sample xn from the incremental proposal distribution. So actually here you should put xni, okay? And no, actually wrong. Sorry, what am I talking about? Let me go back. On the denominator, yes, xn here is the particle, right? The way you can update it. But on the denominator, there is an integral on xn. So this is correct, right? There's no xni. This is an integral on xn. Okay? An integral on xn. All right, and you can, if you are curious, I told you before that when that ratio is is equal to 1, the variance basically is 0. You can actually go back and you can calculate the variance of the weights. You plug in this optimal approximation in 2 lines. You saw that the variance of the weights is 0. So very nice. So the weights will never actually explode. This is really nice. All right, so let's do one example on how you're going to use this in practice. So let's say I give you a problem, and I say the dynamical model looks like this. So transitioning from xn minus 1 to xn is a Gaussian, and I give you the mean to be some function of xn minus 1. The variance is some function of xn minus 1. You can think of this as a random walk or anything you like. That's our dynamical model. And then the observation model, think of y a noisy version of x. So it has mean x and some noise, some measurement noise. And in the equations below, when you see alpha and beta, remember that they're functions of xn minus 1. That's the notation I use. So the optimal distribution is f times g divided by the normalizing factor, which we will normalize things later on. And this is a Gaussian, this is a Gaussian. How do we call the process? We need to get some distribution on xn. Remember when we're killing to death the Gaussians? What's the name? We're going to have to basically come up with a distribution for xn. And I see one Gaussian in terms of xn. And then I see here, this is a Gaussian linear model. This is a Gaussian on yn, but it's linear in xn, the mean. So this is what we call linear Gaussian models, right? So what we will need to do when we expand this, we're going to have to close the square. So when you close the square, it comes out actually that the optimal distribution has this mean value, all right, and a variance that looks like this. All right, so and again, alpha and beta are functions of the previous time. So here's a simpler model, exactly as before, but it's much easier. This is scalar variables. Alpha here is scalar, all right? So the observation model is this Gaussian. The dynamical system is this Gaussian, where xn minus 1 are scalars. So if you apply the previous formula, basically the updated equations are the way you see them on the bottom. So again, this is linear, right? And this is linear. Both models are linear. So for this case, I can come up with a nice proposal distribution that is optimal, and it comes out to be Gaussian. But don't forget, this is linear, and this is linear, okay? In life, not everything is going to be like that. But let me generalize, because you may find this slide useful for your work. If the dynamics are nonlinear, and you have any function f here of xt minus 1 giving you xt, but the observation model is linear, all right, so this matrix C is constant, then actually the optimal proposal distribution comes to be also Gaussian with this mean and this covariance. All right, just manipulation basically of the equations. So really what you need is the observation model to be linear, then you can get very nice answers. You don't really care if the dynamics are linear or not, okay? But if the observation model is linear, the optimal proposal distribution, it's also Gaussian, and you write this explicitly the way that you see here. And actually on later on the slides, in some of the examples, these formulas are being used for particular cases. All right. Now, let me tell you why I call this distribution the optimal distribution, but in some ways you may start questioning, and it's like, yeah, but how optimal is it? And let me put something to question it. So we said at time 1, we sample x1 from a proposal distribution, x1 given y1. So basically, we're going to use information from y1 to compute x1. But you know what? We discussed last week about the smoothing distribution, and somebody will say, wait a second, why is this the right distribution to sample, or the form, and not sample from actually something that approximates P of x1 given all the data up to time n? Right? That is the smoothing distribution, right? Contains a lot of information, so why sample from there and not from there? So you can do this, and you know, it may come up with some new algorithms that may work or not, but here the idea is, if you're going to do something like that, you're not going to be able to do it sequentially. You're going to have to wait to collect all the data, and then you're going to estimate the state after you collected the data, all right? Which in many applications may not be very useful. If this is in robotics or navigation, etc., you want to do things in real time, you don't have the luxury to wait when you collect all the data. So, all right, so let me give you another algorithm that lots of books in statistics use, which is way more easier actually than the optimal algorithm that I gave you. And here is the idea. How about if we use as proposal distribution at time n the actual marginal of P of x? This looks very weird because it says that your proposal distribution was not containing any information from your measurements. So it doesn't matter what you measure, if it is non-linear, linear measurements or whatever, it says the proposal distribution depends only on x's. So, for example, at time 1, this will be the proposal, this is the distribution where you sample your initial state, so Q1 will be equal to that. And if you do a simple calculation, all right, I'm going to give you just the answer. If you do a simple calculation, the optimal proposal distribution at time n that depends on all the previous x's and all the previous, and all the y's, including the y up to this time, it comes out to be equal to the transition probability from xn minus 1 to xn. Okay? So some of you that maybe have used this for homeworks or applications elsewhere, it's very possible this is what you used without realizing it. Okay? So the idea here is, if you do this approximation without any involvement from y's in the way you sample the states x, then it comes out that this incremental proposal distribution for xn that we had before, it comes to be nothing else but actually your transition model from xn minus 1 to xn. And if this is what you have, then the weights actually, you know what? The incremental weights, you remember they were f times g, so if this is f and f cancel, so the incremental weight is actually the observation model. Extremely trivial to program, right? You say, sample the next state from the dynamical problem, update the weights with the, the measurement model, 2 lines, done. Unfortunately, in a lot of problems you can see this will not work because it contains no information from the measurements or the way you approximate these distributions, so it most probably will not work. Okay, so and this is the algorithm basically. Again, you are sampling xn from the transition model. This is how now your previous particles plus this new particle. You increment the weights with the observation model, and the weights basically will be the products of this observation probabilities, if you like. Let me see if there is an example. Actually the example is, okay, 129. So we have some time. So let me just say, this is what people will use, and I believe in the literature, and you should check it. This is what they call the bootstrap filter. I am not very good at these terminologies, okay? I never use them, but if you see the bootstrap filter, they refer to the approximations that we see on this slide, and the importance density basically is not optimal, it's suboptimal, okay? So let me tell you how you can actually take something that is nonlinear, and you can use the optimal filter here, the optimal importance distribution with practically very little type of calculations. And so imagine that you have an observation model, this is our dynamical system, the dynamics are nonlinear, and the observation model is nonlinear. And I told you, there is really no complexity involved in the fact that the dynamics are nonlinear, but there is an issue if the observation model is nonlinear. So if the observation model is nonlinear, you cannot compute this in a closed form solution, this optimal importance distribution. But what you can do is, you can actually linearize this equation with Taylor series expansion. You can make it locally linear. And if you make it locally linear, means you will be able to actually use the equations for linear observation models that I gave you a few slides back. And in a 2 lines algorithm, you'll be able to actually do optimal filtering. And then the only thing you have to do at this step is update the linearization model of the observation equation. So I want you to look at the approximation of the observation model and tell me if this equation makes sense. So we do a Taylor series expansion around the state computed, the state xt computed of the, using the previous state. Can you see this? We say G at xt is G computed, xt is a function of t minus 1, all right? Plus now del G del x computed at this evaluation times xt minus the values of xt computed from the dynamical model, which is like that, plus the noise. All right? So effectively, if you approximate this at each time, right, then what you have is you have a linear observation model, because this function now has become a linear function in xt, and the equations I had for for this optimal importance distribution can be applied directly to this problem. So here's one example, and these examples, by the way, are historical examples. So if you're going to do a homework, and you will, you may want to actually test your algorithms with these problems, because if they don't work for these problems, there is an issue. Okay. So here's the dynamical problem. It's nonlinear. There's a 1 over plus x squared. Okay, but not an issue with the dynamics. But you notice the observation model is nonlinear. Y is x squared. Okay. So the dynamical problem is a Gaussian. All right. From here, this is a Gaussian noise. The observation model is a Gaussian. But it's not a linear Gaussian model because the mean is x squared. So what do we need to do is, so let's say you do nothing, right? And let's say that you are going to use this bootstrap filter. You're going to sample xn, given xn minus 1 from the dynamical problem. That's this distribution. And then you're going to update the weights with the observation model, which is this, all right? So this is the suboptimal filter. The optimal filter cannot be applied on this problem because of this nonlinearity, but this bootstrap filter, you can apply it because the calculation, you can see it is straightforward. So let's see how the results look like. These are the observations, the blue crosses. So these are the y's that I'm giving you. These are the true Markov states, okay? And this is what you get if you try to do this bootstrap suboptimal filter. You get something that looks like that. It actually doesn't look as bad, all right? You are missing a few points here and there. These are the true states, but it doesn't look very bad, okay? And so there is 200 posterior samples that you use here, and I will assume this is the posterior mean basically that you get that looks like that. And if you linearize the problem, there is the possibility of using the optimal filter. And so this morning when I was looking at this equation, it's like, no, this doesn't look right. This is a mistake. So I want you to look at these two equations and tell me that this linearization is correct, actually, especially this term. Where do I get minus f squared over 20? You remember f of x n minus 1 is this thing in the dynamical system, where do I get minus f squared over 20? Remember, the Taylor series expansion says g computed at f at the previous step. So what I'm going to get here is, g is this, so I'm going to get f squared divided by 20 from here. What's the derivative of g with respect to x? What's the derivative of g over divided by, it is x divided by 10. All right, so x divided by 10, okay, times what we have here, f. There must be something here that makes me to get minus f squared over 20. Where did this thing come from? This term times that must be this term, all right? So what is del z over del x? Is x divided by 10, and x is this function here, right? So this is f over 10, and there's another f over 10, so I have minus f squared over 10, and here I have f squared over 20, so the two things combined together, they give me minus f squared over 20. Right, just play with the linearization. So yt now becomes a linear function of xt, and I can use the optimal filter. I can cut and paste the equations that I had for the linearized model from before, for the linear observation model. So the optimal filter, the optimal proposal distribution is a Gaussian. It has this mean, has this variance, it's supposed to be optimal, and there is how the answers look like. I think most of the points look perfect. You can see some points that don't look very good. But remember, it's this is Bayesian. You're not supposed to do curve fitting, right? You're supposed to have good predictive capability, and this looks very good. Okay, this looks very good. And I give you again the general formulas if you guys are interested to linearize. And let me finish with this other very standard problem that they use in econometrics. This is the volatility model. It's like you're observing basically the values of a stock with time, and the observations are a nonlinear function of the state x. Okay, the state x is linear, the dynamics is linear, it's not an issue. But here you have an exponential. And this is a tricky problem because if you have an exponential of x and you do little mistakes in x, it will blow up. So this is a very good problem to actually test algorithms. So what you need to do is, sorry, here I can actually see the calculation is using the bootstrap filter. So basically it samples xn from the dynamical model, okay? And then it updates with the observation model. And so these are the observations. And you notice the observations are very noisy. These are the true states that you try to estimate. And this is how the results look like. And they don't look very good, okay? So this is again, the exact states that you try to match, the blue ones. And the other ones, I don't know if it's red, they look way off. They don't match, okay? So when you test your own algorithms, you may want to try this problem because, okay, the filtering here is not optimal, but the results don't look as good as in the previous problem, okay? They look really bad. And just to motivate the lecture on Thursday, why are the results looking so bad for this problem? So let's concentrate on how, as we increase the time, how, let's say at time 50, the weights of the different particles look like, right? So if you look, when you start, some particles are very big, so this is a nice distribution there, but look at these particles, lots of these particles have insignificant weights. So you are carrying all this calculation, all right? The variance of these weights is very high, so what you need to do is you need to get rid of some particles that have very small weight and resample. And this is going to lead to an essential part of importance sampling here. we're going to have to resample from the important sampling distribution. So effectively, once every while, when we look at the weights and the variance is very high, what we're going to do is we're going to look at the samples and say, can you actually get rid of the samples that have very small weights? Because the idea here is, if a sample has very small weight at time n, it's going to have very small weight at n plus 1. So carrying this with you is not going to be very helpful. Okay, and somewhere in passing, I already talked about resampling. Okay, and we will do this on Thursday. Right? So an extreme idea of resampling, right? If, let's say, this is the approximation that you get with sequential Monte Carlo, and out of all the samples, only one sample actually has significant weight, okay? Then what you do is you get rid of all the other particles, and you only keep one, all right? You keep only one, but this is not very good, right? Because effectively you're going to be left only with one particle. And with one particle, you don't make an approximation, okay? So this can lead to issues that we will see of degeneracy. And I'm going to show you this with a little movie on Thursday on how you can, this issue comes to be significant complication in these dynamical systems. Okay, so let me just define the problem, because we have 4 minutes only, and then I'm going to leave you there. And if you want, I suggest that you read the rest of the notes, so when I come back on Thursday, we can make more sense. Let's say you do, sequential Monte Carlo. You get an approximation like this. You compute the variance of the weights, and it looks very high. So the effective number of samples is really very low. It's not n. So what you would like to do is, you would like to actually resample from this distribution a new set of particles. So you're going to sample particles n out of this approximation, and the new approximation is going to look the way that you see it on the bottom here, where now the new weights are going to be like in standard Monte Carlo, the weights are going to be 1 over n. Okay? And if you're going to sample from this distribution, this is like a discrete distribution, because you have these particles, and some particles have very high weights, some have very low weights. So when I say sample from this empirical measure, how are you going to do that? Can you guess? Looking at the equation on the top. So I have a distribution that says this particle has this weight, this has smaller weight, this bigger weight. So how do you sample from this distribution to get an approximation that looks like that? And again, it would be like sampling from a discrete distribution that takes this discrete values I, and what is how are you going to sample? What's the key word here? Again, one sample has very high weight, so you want to sample more of that. Others have very small weights, you never want to sample. So you're going to sample this x curly I in proportion to what? To the weights. Okay? So you're going to sample this in proportion to the weight. So effectively, you're going to be sampling from a multinomial distribution that is defined by the weights, basically W1, W2, etc. Okay, and there are multiple ways of doing this. So actually the calculation is only one line to sample for this. And we will see the good things that come from resampling in the context of the variance, but also we will see the bad things that come from sampling and this degeneracy issue. And just to leave you with some imagination on what is going on. This blue is a proposal distribution defined in terms of these particles, these delta functions. We really want to sample for this red distribution, okay? And with resampling effectively, so you can see some of the weights are significant. So we're going to resample the approximation, and then effectively you get the distribution that looks, So some of the samples, basically with high weights, stay there. The others are killed. Okay, we will see this in detail again on Thursday. There are way many more things on the slides. Please look at them. There are applications in multiple areas, all right? Because these are generic problems. So take a look on the slides, so we can try to finish them on Thursday.
Why don't you check? Did you get back with that guy yet?
Tell him to call me.
I'll tell him to call
Tell
you.
him to call me.
Okay, good.
Okay.
He's still interested.
No,
He's
tell
still on
him.
the hook. Yeah.
By the way, there is another student from Duke who is in biostatistics finishing his master's, and he told me he's very interested to come and move here. But so maybe you know the guy, so I'm going to forward you his email,
Okay.
and you guys can. Take it up because I don't know with whom he wants to work or.
Yeah, sure.
So,
Awesome. Yeah.
And he has a
I worked with-
master's. He says he has a master's.
Yeah, it's been a while since I was at Duke, but yeah.
Yeah.
Good. Okay.
Maybe
Yeah.
he's looking for you.
Who knows? Yeah. Okay, man.
All right.
Good. All right. Cheers.
Yep. See you
Everything
Thursday.
okay?
Surviving.
Okay. Good.
All right. That's the word.
Yeah.